Hello everybody. My name is Phil Steinhorst and I'm a PhD student from University of Münster. In this video I present our work on revisiting self-efficacy in introductory programming. Self-efficacy, as defined by Albert Bandura, refers to beliefs in one's capabilities to organize and execute courses of action required to produce given attainments. Research in various fields, also in computing education, has shown that it goes hand in hand with other non-cognitive concepts, making it crucial for educational research. Looking at prior literature, one can find both general instruments as well as instruments tailored to specific course contents used to measure self-efficacy. For introductory programming, the best known instrument is, without doubt, the Computer Programming Self-Efficacy Scale, developed by Ramalingam and Wiedenbeck in 1998. The original instrument consists of 32 items that have been used by researchers in two ways: comparing all scores item by item, or calculating an average score over all items. But there's also a third alternative. Ramalingam and Wiedenbeck reported on 4 item groups called factors, which could be used to aggregate scores of subsets of items. However, to our knowledge, no researcher has used this type of scores, and we even have anecdotal evidence that researchers refuse to use them. To understand why this could be the case, let us take a little detour first for a simplified introduction what factors are about. Imagine you wanted to assess self-efficacy in your gardening class. Since different plants require different treatments, you created an instrument that asks the students about their confidence in growing each of them and administered it in your course. Now, you might wonder if there are items measuring a common underlying construct and that can therefore be combined. For this, there is some statistical magic that tells you which items are somewhat correlated with each other. These subsets of items are called factors, and the process of finding these factors and interpreting them is called exploratory factor analysis. The factors are often ordered by the total variance explained. This means the items of the first factor, here in purple, account for most variance in all the observed variables. Instead of comparing values item-wise, say over the course, you can now stick to a much smaller number of derived variables. If you repeat the measurement at the end of your course, you might find a stronger increase for the growing vegetable factor, since this topic was focused in the second half of the course. You might also see that the variance explained by each factor changed, as depicted by the different colors. But as long as all item groupings are still stable, your factors work as desired. However, this might not be the case when considering a different population. If you repeat the process with a second sample, you might get a different factor structure, because other items turn out to be correlated, as shown by the crossing lines. In this case, your factor variables found in sample 1 would have little informative value for sample 2, and comparing them across the samples would make no sense. This could happen, for example, because the courses differ in their contents, or simply because both populations have a different understanding of the terms used in your instrument. Therefore, working with factors can be helpful because it reduces your data to essential things, but it can also lead to invalid results, risking to compare apples with oranges. Back to the CPSES. As mentioned before, researchers neither used factor scores nor revisited the factor structure of the instrument. Hence, we thought it would be time to do the latter. We administered the original instrument in 2 offerings of the same course at Münster. The courses started with Racket in a How to Design Programs fashion, followed by Java. For 2016, we found these factors. Comparing them with the original factors, one can not only see many items forming new groups, as illustrated again by the crossing lines, but also changes in the total variance explained, as indicated by the difference in factor coloring. Items that explained most of the variance originally now explain least, and vice versa. The same effect can be observed with the 2018 dataset, but it gets even worse. Ignoring the original factor structure and comparing only the 2 Münster datasets also shows striking differences in the composition of the factors as well as the variance explained. Keeping in mind that both courses follow the same syllabus and only differ in the instructor, this difference cannot be explained by a difference in contexts, but would indicate a weakness of the instrument itself. To verify that this phenomenon is not specific to Münster, we also ran factor analyses for 2 Python-based CS1 courses which also showed that the original factor structure is not suitable. We conclude that factor structures of the CPSES tend to be unstable even when considering two educational contexts that are as similar as possible. Hence, comparing self-efficacy scores on factor level is categorically impossible with this instrument. Since we have seen that the standard instrument for assessing self-efficacy in introductory programming is not very robust when it comes to factor level scores, we ask the question if it is even possible to build an instrument that both measures self-efficacy and provides a stable factor structure. And to address this question, we tried to build such an instrument from scratch. Let us first take a look at the requirements for a new instrument. Our goal is to design an instrument that measures self-efficacy in introductory programming courses. We want it to be multilingual and multi-paradigmatic, to make it widely applicable for many CS1 course designs and contexts. To ensure that an instrument indeed measures what it is intended to measure, we have to talk about validity here. We discuss validity evidence, as this practice is recommended by the standards for educational and psychological testing. There are 4 sources of validity evidence to be considered: test content, response processes, relations to other variables, and internal structure. I give you an understanding of our instrument design by quickly addressing these 4 criteria. The first criterion refers to the relationship of the content of an instrument and the construct it is intended to measure. Since the instrument's items must reflect the contents typically taught in a CS1 course, we use literature on important concepts, curricular standards, as well as sample course descriptions as a foundation for creating the initial item pool. After removing language and paradigm-specific aspects, the initial item set was reviewed by experts experienced in teaching CS1 with various languages and paradigms, resulting in 25 items for the final instrument. Since the instrument design is therefore based on previous work, curricular standards, and expert judgment, the content of our instrument contributes evidence of validity. Next, we discuss the response processes. For the scale of our instrument, we followed Bandura's recommendations for a Likert type scale and aligned the answer options with the CPSES to allow for comparison. We further added a preamble giving cues with respect to paradigms and how to interpret the scale values, and added a no answer option and a text field below to allow for comments on terms that might be unknown or ambiguous. Since we received no feedback on unknown terms by the participants, we have no concerns that the response processes could compromise validity of our instrument. In our paper, we thoroughly discuss the relation of our instrument's scores to other variables by addressing convergent and discriminant validity, test criterion relationship, and validity generalization. To cut a long story short, we summarize that all results conform with what has been stated in prior studies or in self-efficacy theory. Now we discuss the internal structure of our instrument, which brings us to the issue of factors introduced earlier. To see how our instrument might factor in different contexts, we assessed it in 3 course populations. The courses in Toronto both were imperative object-led introductions to programming taught in Python, while the course in Brown was a Java-based follow-up to an HTTP-like functional programming course. We ran an exploratory factor analysis with a combined dataset from all 3 courses and obtained 4 factors: tracing program flow, using structures and patterns for problem solving, persistence, debugging and problem solving competences, and controlling program flow. Following standard practice and recommendations, a few items, shown in black, were not retained due to ambiguous loading and to improve interpretability. Our factors reflect typical activities students undertake while learning to program. Both conformance with the underlying construct and high values of Cronberg's alpha show validity evidence on internal structure. Finally, we analyzed the suitability of the factor structure in each of the 3 course populations separately, since we aimed our instrument to be multi-paradigmatic and multilingual. Numerical values obtained from confirmatory factor analysis showed superior fit for both Toronto courses, but, judging by the numbers, the fit for Brown appeared to be less good. Let's have a closer look why this is the case. As we did previously, we used an exploratory factor analysis to compare both factor structures and visualize the differences. This time we see no crossing lines. The EFA shows almost the same factors. The picture gets even clearer when you remove the previously dropped items from the Brown factors. The factors are identical now, but as can be seen from the differences in color coding, they explain different amounts of variance in the two populations. However, remember the gardening example in the beginning. This is both appropriate and desirable, as the reordering reflects differences in the experience and training of these students. At Brown, the HTTP approach emphasizes problem solving using structures and patterns from the very beginning, so the students have extensive mastery experience. It is natural that the factors corresponding to problem solving account for less variance here. To summarize, it's important that, despite the differences in the two populations, the instrument demonstrates a stable grouping of items into factors. Given the differences in approach used, it's also encouraging that the variance explained by the individual factors varied. This suggests that factor scores of our instrument can be used to investigate these differences. In conclusion, we have developed an instrument for use in introductory programming, and we have shown that, for the population studied, it behaves as one would expect from an instrument measuring self-efficacy. The items in our instrument were derived from research literature, and our instrument is multilingual and multi-paradigmatic by design. This reflects a variety of ways in which CS1 can be taught these days. Most importantly, and in contrast to previous work, our instrument factors stably across different populations. Differences in variance explained thus can be used to understand different emphases in teaching. We note that the validity of our research crucially depends on the fact that the courses followed roughly the curricular recommendations given in the literature used for construction. Also, where our combined study population was rather large, a common trait was that all institutions were research intensive. We therefore recommend that scores reported from using our instrument should be reported along with both curricula and demographics. In particular, this applies to scores on factor levels, and we look forward hearing about any revalidation studies. Thank you very much.